A process requires typically more than one frame to properly execute. For example, in the IBM 370 computer systems, the SS move instruction, which is a single instruction actually, might require at least 6 frames because the instruction itself is 6 bytes, so it could be starting at the end of one page and the beginning of the continue in the beginning of the other page, so it could be spanning 2 pages. Similar would be true for the from address and the to address in the move instruction. So in total, at least 6 frames should be allocated to a process for the move instruction to successfully complete. Now, this is the minimum number of frames. How about the maximum number of frames we should be allocating to each process? There are 2 major allocation schemes. One is the fixed allocation and the other one is the priority allocation. Of course, there are variations of this. In the fixed allocation, first thing you can do is you can give equal share to everyone. Like depending on the number of frames available, of course excluding those used by the kernel and system services, but you can divide it to the number of processes and give every process an equal share. This appears to be fair, but actually it's not, because there are some processes that could survive with few frames, but some processes are inherently very large and they could require much more frames to properly execute. If you give everyone the same share, some processes could be executing very fast while others are quite slow. So the solution to that would be proportional allocation. Depending on the size of the processes, you give some share, some different share to each process by just looking at the ratio of the size of that process against the sum of all process sizes, as shown in the slide. You can do the similar thing, not based on the size of the processes, but on the priorities of the processes. So if a process PI generates a page fault, you could try to do a replacement within its own frames, but if not, you could also be stealing a frame from a process with lower priority. But are you going to allow a process to steal frames from other processes or not? That depends on whether you're applying global replacement or local replacement. In the case of global replacement, a process is allowed to do replacements among its own frames, but also be allowed to take frames from a larger pool of frames, including the frames of other processes. This results in better throughput for the overall system. However, depending on from which process you're stealing these frames, the process that steals the frame, of course, performs better, but the other poor guy who loses a frame now could be suffering. So the execution time could be varying significantly depending on the process. On the other hand, if you use local replacement, the processes are not allowed to steal frames from each other. So per process performance would be more consistent. However, the overall system performance in terms of memory utilization could be suffering. Now, so far we have assumed that memory access is equal for all cores or CPUs in the system. However, remember we earlier discussed the non-uniform memory access, NUMA, where you have multiple processors or cores where the capabilities of these processors are different, and also they might have their local memories which they can access faster. They're allowed to access the memory on other CPUs, but that would be slower. So in such system boards with multiple CPUs with different properties, the optimal performance depends on how the threads or processes are scheduled to these cores or CPUs. For example, in Linux, the scheduler pays attention to this and tries to schedule the same thread to the core that it was previously scheduled to. Now, in memory management also, in addition to the scheduler, in memory management and virtual paging, if you are careful to assign these pages to the frames that are associated with that core, then the performance would be significantly better. Solaris does it in a similar way, but under a different name, by creating what's called L groups. So it has a structure to track the CPU per memory latency groups, and the scheduler and the pager works by paying attention to this. But the concept is similar to what Linux does. Now, so much with the frame allocation, but there is a problem we call thrashing. Now, remember that minimum limit. It's not only per instruction, but consider, for example, a function which calls, for example, maybe many other functions, or it could be accessing many variables which are in different places in memory. Like local variables are remembered in stack, globals are in the data segment. Also, if the data segment is too large and variables are on different pages of the data segment, you need many pages for the proper execution. Maybe not in the same instruction, but instruction after instruction, you sometimes access this page, sometimes this one, sometimes this one. Now, if you're not assigned sufficient number of frames, when you try to access different pages for the instructions and also for the data, you might be causing many page faults. You might end up in a case where you have you're causing so many page faults that you're always actually trying to do page in and out operations. The problem now suddenly starts building up, because one process, when it starts causing a lot of page faults, it will cause queuing at the swap device, because it's asking for too many page in and out operations. Now, this will affect the other processes that also want to do that cause page faults, maybe once in a while, not that frequent, but once in a while. But since there is a long queue there, they will also be waiting for the swap device, and this queue will get longer and longer. Now, since the processes that are waiting for the swap device are removed from the ready queue because they're waiting for the swap device, the number of processes in the ready queue will drop. The operating system will detect this, and to increase the number of processes in the ready queue, it will try to increase the degree of multiprogramming, and it will try to bring in more processes into memory. Now, this will cause even more page faults, because these processes, when they want to start, due to demand paging, they will cause more page faults. So the queue will get even longer. So the operating system decides to increase the degree of multiprogramming even further, because utilization is dropping. And we're now in a cycle where we're actually causing more page faults, increased degree of multi-programming, so more page faults, further try to increase. This is called thrashing. Actually, suddenly the system starts doing more swap in-out operations because the CPU utilization has dropped, which further causes more queuing at the swap device, therefore even lower CPU utilization. So the system stops doing useful work and rather deals with swapping operations, which is actually overhead. So less useful work, more overhead. And this goes worse and worse and worse. So this state is called thrashing, where the process is not a single process, but most processes are busy doing swapping rather than useful work. So this is actually showing what's happening. Normally, we would like to increase CPU utilization, so we allow more processes in the system, which is increasing the degree of multi-programming. As we increase the degree of multi-programming, the CPU utilization gets higher and higher. However, after some point, the processes will not have sufficient memory. Okay, therefore, they will start causing page faults. Page faults will put more burden on the swapping device, so the queue for the swapping device will increase, and the system's CPU utilization will start dropping, but the operating system misunderstands and tries to increase the degree of multi-programming even further. And this makes things even worse rather than improving. So suddenly the performance of the system significantly drops, and we say the system goes into thrashing, something you should be very careful with. At that point, you will realize that your computer seems to be stalling, like freezing, and if you have a regular hard disk rather than SSD disk, because the SSD disk does not make any sound, but the regular hard disk does, you will hear that the computer system is using the disk. You hear the sound of the disk spinning and the read-write head moving, but in fact, on the screen you see that the system is almost frozen. So this is the state of thrashing. So why does the demand paging work? Demand paging, remember, depends on locality model, which means the process at any point in time is not executing instructions from everywhere, but it is executing instructions in some locality, typically in a function, for example. So it is executing instructions in some locality, and also the data it's using are in some locality, not actually in a single locality. The process could be using some data from here, and some from here, and some from here, but not the whole data segment and stack, for example. Not all local variables and the global variables, in other words. And the system could be in this locality for some time, but then this function will end and the process will jump to some other function. So suddenly the locality will change. Also the data it requires might change. But again, once it moves to a locality, it will remain in that locality for some time. So if we plot it, now here the y-axis shows the memory addresses, therefore also the page numbers. So you can realize that, let me pick up my pen. You can realize, now if you take a point in time, let's say this point in time, you realize that the process is making use of the statements, memory locations here and also here and little bit here. However, if you move in time, and later, if you look at the locality, we see that the locality is here, a little bit here, now here, and a little bit here. Now, you can see some overlap in localities, like there is some overlap here in this region, and there is some overlap here in this region, and slightly over here in this region. But the locality is actually changing in time. So for us, it would be nice to know the set of pages that we need to keep in memory for each process. So for this, we set up what's called the working set model. We create a working set for each process. Now note that the working set for each process is different. Even the size of the working set is different. Actually, the working set size is different for the same process depending on the time. Now, to talk about the working set, let's first define the working set window. The working set window is the length of time, or the number of page references, the last page references. For example, let's say we're interested in 10,000 instructions. That means we would like to keep the pages that were accessed in the last 10,000 instructions. So delta is this value. We're interested in the last 10,000 instructions. Now, in the last 10,000 instructions, in the last 10,000 memory accesses, you could have, so delta is this length. If you look at this time duration for those 10,000 instructions, you have accessed the pages 1, 2, 5, 6, 7. Okay? Whereas if you look at the same process, again 10,000 instructions, but at some different time, at time t2, in the last 10,000 instructions, you have accessed only 3 and 4. So here the working set would be 5 pages, whereas here it's only 2 pages, same process. Okay, even in the same process, the working set differs, even if you look at the same 10,000 last 10,000 instructions. So one thing is, how large should this delta should be? If delta is too small, it will not be able to look at the entire locality. Like if, for example, you make delta, let's say 500 rather than 10,000, if you're in a function and you need different memory spaces, in the last 500, you will not be keeping the information about all of the real accesses. You're just looking at a very short duration. For example, here you might see only 5 and 1, although recently you have been accessing also 2, 6, and 7. If it's too large, then it will span several localities. It will not harm that process, but overall, if you consider a very large locality for that process, that means you're missing the locality. You will not be able to store the pages for the other processes, so you will be harming the others. Okay, so we don't want delta to be very small. We don't want delta to be very large. And the length of delta determines the working set for each process. Let D be the sum of the sizes of the working sets for all processes. So it's the total demand for the frames. If D is larger than the number of frames in memory, that means in the last 10,000 instructions, the number of pages that were accessed is more than the number of frames we can have in the memory, that means we're running into thrashing. So if D is greater than M, we should decrease the demand. And the way to decrease the demand is suspending. Let's pay attention, not terminating. So we are not killing processes, but we're just suspending them, putting them into sleep, suspending some of the processes and swapping them out of memory, so we open up more space for the remaining processes. This way you can cope with thrashing. Now, if you look at the working sets and the relationship with the page fault rates, if this is your working set time, your delta, you will realize that when you enter a new locality, like when you make a function call, suddenly the process will start doing a lot of page faults because the instructions for that function are in a different place, are in different pages. Also, the variables that function is accessing are also in different pages, so that change in locality suddenly will cause a lot of page faults. So this is what you see in here, that increase. But once you have faulted for all those pages that were required, you will be able to survive with the existing pages in memory for some time. So you suddenly go up some hill and then stay in a valley, because here in this area you're not causing any more page faults, you're just making use of the existing pages. But then that function will end and you will jump to another locality, and again an increase, and then a valley. So it's just some hills followed by some valleys, and this structure repeating over time. So somehow we need to keep track of the working set. To keep track of the working set, we need some interval timer, like delta, as we said. Let's say it's 10,000 instructions or memory accesses again, and some reference bit or reference bits actually. So for the sake of the example, let's say our delta is 10,000, and we also set a timer, let's say every 5,000 time units. And we're not using a single reference bit, but 2 in-memory bits, and we also have the current reference bit. So including the current, it makes 3. So whenever this timer of 5,000 time units expires, you copy the current reference bit into one of these memory bits by just shifting them and resetting the current reference bit back to 0. So this actually shows, like, the current reference bit shows the time from 0 to 4,999 time units. So the current, let's say, the last 5,000 time units are in the current reference bit. In the 2 in-memory bits, you have the reference from 5,000 to 10,000 and 10,000 to 15,000. Okay, so this way actually you have some information for the last 15,000 time units. The current reference bit will be 0 for a specific page if it has not been accessed in the last 5,000 time units. But if it was accessed, let's say, between the time units, in the time units between 5,000 and 10,000, the first in-memory bit would be 1. If it was also accessed between 10 to 15,000, the second in-memory bit would also be 1. Or it could be 0, 1, 1, 0, 0, 0, whatever. So this way you have some information about what has been going on in the last, in this example, 15,000 time units. Note that this is not completely accurate because it doesn't say in those, let's say, 5,000 time units range at which point there was an access or how many times there was an access. It just shows whether there was at least one access or not. So it's not very accurate. You can improve accuracy, if you wish, by having more in-memory bits. Like instead of 2, you can have 10,000 memory bits and make these timer durations shorter. Let's say 1,000 instead of 5,000. This way you can keep better track of the working set. Now, this approach, keeping track of the working set, is nice, but it's an indirect way of actually controlling the page faults. You can do it in a different way. If you can keep track of the frequency of page faults, you can define an upper and lower bound for the page fault frequency. If it falls below the lower bound, that means you have so many frames allocated to this process that the frequency of page faults is very low. So that means you have more than enough frames for this process. That's why you have lower page fault. So you can, for example, decrease the working set size for this process and give those frames to other processes that have higher page fault frequency. On the other hand, if a process's page fault frequency is above the upper bound, then you are in a trouble. You have already transferred some frames from the processes with lower bound to these processes with higher page fault frequencies, but still it is above the upper bound, and that means you're going into thrashing. In that case, you take the precaution for thrashing, which was, remember, pick one process and pause that process so that you can use its frames for the other processes. This way, decrease the degree of multi-programming, but improve in terms of page fault frequency, and thus avoid thrash.